So what is RAID? So RAID is a MapReduce conflict project, and we have been working on RAID because we want to save space. So why is saving space such a big deal? Because HDFS has a default replication of 3, which means for every byte that you write, you effectively use 3 bytes on disk. And for a gigabyte scale or terabyte scale, this might be okay, but when you go to a petabyte scale, like at Facebook, this becomes a big deal, and there's a lot of cost that needs to be accounted for. So RAID helps us save space by essentially reducing the replication of each file that we store. So in 2 sentences, if I were to explain, this would mean we reduce the replication and find some other way of maintaining the data safety. So in our case, data safety means using parity files. So let me explain what that means. So right here, this is an example file. It has 10 blocks, and it has a replication of 3. So for each block, you have 3 replicas and a total of 30 replicas. So we want to get this down, and so let's look at this example now. We set the replication of this file to 1, right? So each block has only 1 replica. But to maintain data safety guarantees, we also create additional parity blocks. So to get an intuition of what parity block means, think of XOR, right? So if you have 10 blocks and you compute XOR of those 10 blocks, the new block that you get can be used as a parity block. And if you lose one of your original blocks, you still have the 9 other blocks and 1 new parity block, and if you XOR them all back, you get your original block. Right. So extending this to a more general case, like you take Reed-Solomon for example, you can create more parity blocks and tolerate more failures. But the replication has come down to 1. So from an earlier replication of 3, we are now at 1.4. But we have increased our data safety from 3 failures to 4 failures in this case. So Scott will be talking a little bit later about how we get the data safety. So let's move on to the next part. So in the remainder of this talk, I will call the original file as the source file, and the parity blocks that are generated are kept in something in a parity file. In terms of data size, Facebook has the biggest Hadoop cluster. The user data is about 10 petabytes, and in terms of raw usage, that would be about 30 petabytes. But by using RAID in our data warehouse, we have saved about 5 petabytes. And that's a big deal. So, if you're curious about how we went about doing this, it didn't happen overnight. We have been deploying RAID for about 4 months now, and we started with a few tables in the warehouse, and gradually increased the scope as we gathered more data. So right now we are at 5 petabytes. So let me show how this looked like a month back. So this is a graph that shows the savings from using RAID in our warehouse. A month back we were at about 3.5 petabytes, and as of yesterday it's actually a little bit more than 5 petabytes. So in terms of deploying, so it doesn't have to be something that's done all of a sudden. People can try it out and see if there's an impact. So move on to the anatomy of RAID. So RAID has both server-side and client-side components. By server-side, I mean the HDFS cluster, and by the client-side, I mean the people who actually read the data. On the server side, there's a new daemon that we introduced. This is called the RAID node daemon. So think of it like another a job tracker daemon or name node daemon. So this can run on any of your existing machines, or in our case we have a dedicated machine to run this daemon. One of the most important components inside this daemon is the block fixer. I'll explain in a little bit why we need to fix blocks. And then the next component on the server side is a block placement policy. And so this component determines how you place the new parity blocks or the existing source blocks. The client side has two main components. One is a file system. So we have modified, rather implemented a layer on top of the existing distributed file system. And this lets clients access rated files without knowing that they are actually rated. So if a rated file lost blocks, this file system would be able to reconstruct those blocks on the fly without any interruption. And then there is an administrator tool called RAID shell. Think of it as a RAID equivalent of the standard FS shell. So this lets us do an FSCK for RAID, and it lets us fix blocks on demand. So here's a picture that kind of shows what I just said. So you have your main node, and the RAID node is a new machine that we introduced. The RAID node primarily interacts with the name node. It finds out what files need to be rated, and it also figures out what blocks need to be fixed. Once it figures out what blocks have to be fixed or what files have to be rated, the RAID node has a choice. It can do all the work by itself on that one machine, or it can use the existing MapReduce infrastructure and submit a MapReduce job to get a greater throughput. And on the client side has the RAID file system, like I said. That's this one here. And the RAID file system again behaves like a standard distributed file system, except that if there are missing blocks that can be fixed using RAID, it does that and allows the tiers to proceed. So some more detail about the RAID node. So like I said, it's a daemon that figures out what needs to be rated. So the way it does it is not by scanning the entire file system, but it takes hint from a policy file and uses some file patterns to determine what files have to be rated. And then once it generates the parity files, either through the MapReduce job or local job, it then reduces the replication of the file that has been rated. So one thing you might have noticed is that I said there is one parity file for one source file, and that has a couple of implications. One is that for once a source file has been deleted, the parity file is no longer useful, so it needs to be deleted. So that's one housekeeping kind of job that RAID node has to do. And the next one is that if you generate one parity file for every source file, that in effect you're doubling the number of files in your file system. At a small scale this might be okay, but at Facebook's scale, where we are pushing the limits of a 70 gigabyte machine, we cannot afford to double the number of files. So the RAID node creates a HAR archive out of the parity files, and what that means is that the number of files is reduced because multiple parity files get combined into a single HAR file. So we keep the number of inodes in check this way. So if there are any questions, I'll talk about the block fixer.
What's the performance impact are you having by having to do parity and data writes?
So the question was, what is the performance impact of doing the parity and data writes? So when the file is originally created, we don't write the parity right then. So when the file is created, it is created as a default replication 3 kind of file. And the RAID node comes in after the fact asynchronously computes the parity files and then reduces the replication. Question?
Is there any reason you didn't use read-free erasure code like fountain codes?
Like what code, sorry?
Fountain codes. Fountain.
Well, so we based our work on research from CMU. So the idea there was that you can reduce the replication to and use any other erasure code. So I'm not sure what fountain code itself does. Maybe we can talk offline.
Replication is important for reliability, but also for average performance. Like if you have multiple blocks running, they can use different machines, they can pick up the same process. So in this model, you use that. So is there a performance impact on the average job when it is there?
That's a good question. So the question is there an impact on MapReduce performance if you reduce the replication? So what we use in Facebook right now is XOR-based rate, where we reduce the replication to 2, not 1. So there are still 2 replicas available. And what existing research has shown is that having 2 replicas instead of 3 does not reduce the performance that much. So it is probably a 10% performance impact. Now if you go to Reed-Solomon encoding and reduce the replication to 1, yeah, there will be a performance impact, but the expected use case is that we will only use Reed-Solomon for archival kind of mode, where the usage will be less.
How do you handle, you go to 1, you start using servers, how do you handle that data loss?
That's the next step. So, like you pointed out, there's once you have only 1 replica and a block was missing, the neighbor can do anything about it. You cannot compute the block. So the block fixer component identifies such missing blocks and it deconstructs those blocks by looking at the parity data. Right, so we have a thread that periodically retrieves a list of corrupt files from the name node, and the block fixer can then deal with source blocks and parity blocks in 2 different ways. If a source block has to be reconstructed, it's what's called a decode operation, where we use the parity data and do the reverse operation of an encode. Right? And if you have to compute a parity block, then that can be done by just the same operation that was used to compute the parity file in the first place. So it's just creating the parity file, but at a block level. So we have code that does both of this, and the block fixer has both a local and a distributed implementation. So even if there is a spike of hundreds or thousands of missing blocks, our implementation of the distributed block fixer can handle it and fix the blocks as fast as the MapReduce job. So we have seen like 1,000 blocks being fixed in 10 minutes. And even if there is a client that tries to access that file while it's being reconstructed, the client file system can reconstruct blocks on the fly. So Scott will be talking about that a little bit later. So I talked about parity hards a few minutes back. So parity hards make life really difficult for us because you're combining multiple parity blocks into a single parity hard block. So just to give like a feel of what I'm talking about, a parity file block size could be like 256 megabytes. Right? But once you hard them, the hard could have a block size of a gigabyte. So you have 4 parity blocks in one hard block. And if that one hard block goes corrupt, then you have to fix all those 4. So this block fixer is sophisticated enough that it can identify what parity blocks need to be fixed, and it can take care of fixing that hard block also. So here are some statistics about how our block fixer has been performing. So as you can see, in the past few weeks, it has been working pretty hard for us. In one particular day, there were about 500 missing blocks that it fixed. More recently, just like a couple of days back, I had a incident where there were about 1,000 blocks. So we have this in production, and it's working pretty well. So far, I've been talking about the general architecture of RAID and how things work at high level. Scott will talk about the cuts and details.
Okay, so the erasure code is the underlying component for doing the recover for the bytes, for the symbols. So we have this class called erasure code. It's an interface. It's an abstraction for this erasure code implementation. So it has the interface of taking an array of message and generate parity files. And these are actually bytes. And right now, the setting we're using is we take 10 message and encode to 4 bytes. So 10 bytes to 4 bytes. And this is the interface for the code. This data is a combination of these two. So in that case, there will be 14 bytes. And erase the location will show which bytes in this array has been erased. Then this is a return value that recovers these locations. And right now, the implementation we have is exclusive overcode and read-only code. So there are people mention fountain code. In the future, we can make this pluggable, and then people can implement different codes here. I'd like to point out that this is different from like usual erasure code people use in communication. Because in this use case, the block length is really short. It's only 10 blocks. If you try to increase it, then fixing a block will become very difficult. For normal case like LDPC, people use thousands of the block length equals thousands. In this case, you have to fetch, in order to fix one block, you need to go to 1,000 machine and get that block. That's almost impossible. So in this case, the block length is really short. So it's different from other use case. In other use case, there are many like fancier code. In this case, I will say these are like a good candidate for this kind of use case. And there are the other two components called encoder and decoder. They still use this one to talk with the HDFS. So the HDFS will encode blocks and files. This one will use that and transform them into bytes and use this to encode code. So I'm going to talk about block placement. Before that, we can see one example. So this is one file that has 10 blocks. And in the right now, if you use a replication of 3, it will be 30 blocks. And for this case, we have replication equal to 1, and we create 4 parity. So this is the parity file has 4 blocks. And in this case, we can correct any two failure. So we have two data node dies, and we can use this block to recover these two. In this case, we can cover up to 4 errors. So the error actually, we can recover much more failures. So if there are 4 errors, then we can recover this 4 by looking at other blocks. So you can see that there's a dependency here. Like this one can fix these two. So there's a dependency among these blocks. There are dependency among these blocks. Because in order to fix this guy, we need to look at others. And this is a new dependency introduced to the file system. In this case, Nano will put these 3 blocks in different locations. You will not put those 3 blocks on one node. So if you lose that node, you lose 3 blocks. There's no point to put them same node. But in this case, Nano doesn't know these are dependent. So Nano might just put these 14 blocks on one machine. And that machine dies, you lose everything. So that's why we need new block-based blocks. So
parity slice your nodes.
So
in other words, do the nodes as a bit slice.
So
the other question is, are they just attached to your nodes, or are they going to press
I guess the question is why do we build the parity inside the block, right, along with the file? So the reason why we do this, so the other way to build this, like you can build the parity inside the same file, so that in the file you have blocks, you have parity blocks, and then no will know these are from the same file. So the reason why we do this is major because this is a country project. So because it's a country project, we don't want to touch any part of the name. So these are entirely outside of the option when we're not changing one line of the code. So all we do is we look at the file and we generate another file called parity file. And for the array file system, right, another file system, when it reads this file, find is corrupted, it will go to the parity file. It has a way to find out where is the parity file and fix it. So the reason we're doing this is we entirely build it outside of the HDFS. So if we design this from scratch, we could build this inside the file. It will be much easier. That's a good point. So the default block placement policy is for array because it doesn't know the logic for placing those blocks. So the source blocks can sit on the same line. So source block itself can be sitting on the same node, and parity blocks also. And also they can blocks from different files can sit on the same node. So what this policy does is for source file, this is it's important that we don't impact the performance for using this rate. So what we do is for the first time we write it uses a default policy, so it has a default performance. This is actually quite costly. For every block you write, you have to figure out where are other blocks. You have to go to name node and do a lookup. It's very expensive. So for source file, we write it using default policy. Only after we rating it, then we move the block around so that they don't sit on the same node. And for parity file, when we actually generate this parity file, we'll control the placement. So if you're aware of other files that can be decoded together, and they will not sit together. So okay, let me talk about the client side for the array file system. So this is a file system that knows where the parity file and source file is. So it allows the client to read it. Some corrupted, like a file might be considered by name node as corrupt, but it actually can be fixed by the parity file. So what it does is you catch a block missing exception and checksum exception. Then it has its own logic to figure out where are the parity files and where are other blocks related to this block. And then you'll do the decode. You use the erasure code to decode it. But one thing we do here is we will not fix that file after we read it. We'll just generate that file. So the reason why we do this is we don't want it to read and write at the same time. So to be able to fix it, one thing is the block fixer that wrong code. The other thing is we have this client pool called ratio. So it can be, it's an administration pool. And it can use to recover a block. So you can, if you see a corrupted block, you can just use a command line to fix it. If you find block fixer is not fixing it, you can just do it yourself. And it also has this FSC kit. It's done by our intern Patrick. So the reason why we need this is the normal FSC kit doesn't know this logic about rate. So if you do FSCK, you'll see a bunch of corrupted files, but they are not actually corrupted because they have parity files. So what this one does is it knows the parity file, and you actually compute it to see if one file is actually corrupted. And it's a good tool for an administrator to fix files and discover corrupted files. So I guess for users, people are interested in how to use this stuff. So to use this, we have one configure file called RAID-XML. So this is the only additional configuration file we need. So inside this file, you can specify multiple policies. So inside the policy, you specify the file pattern, so the directory pattern. That's a file you're going to read. And also the type of code you want to use. And the final replication number. For example, you want to put 1, and put the resolve code. And specify a pattern for the directory. And for the HDFS config file, you need to specify so that we know where is that RAID.xml file. And we also need to specify a location for parity files. So this is why the file system know where are these parity files, because it knows the directory. And you also need to specify to use a RAID file system and use a RAID block placement policy. And then there are scripts to start network. So you can easy way to use this is just copy and paste it into start network. So when you start the whole cluster, RAID node is running. And this law you need to use this use HDFS for. So more details are on the wiki. That's it.
What's the size of the network? How many CPUs and how many files does it?
So the question is, what is the configuration of our RAID?
So the RAID node is a fairly low-cost machine. It's not very CPU intensive. So whatever you could use for your data node, I think it will work fine. It doesn't need too much memory either, so not like the main node. So I think a data node caliber machine would be enough. It can do, let's see. So since we had a staged deployment, we didn't have like the entire warehouse in one go. So it's tough to say like what's the max it can do. But I have seen at least like 10,000 files per hour, or maybe even more than that.
So we actually have a way to control the RAID job. Because if we don't do anything, then you'll submit a huge job, and then that will take out the entire cluster. So because we're using fair schedule, so we also specify a pool. So in RAID config, you can specify a pool that we use. So if you limit the throughput of it, like does not affect other jobs. The question is how many parity fits do we use? So for our current we have two configurations. One we use exclusive board, the other is a resolve. So for exclusive board, the block length is 10. So we take 10 blocks, it generates one parity block. So for the resolvent, we take 10 blocks, generate 4 parity blocks. So the redundancy is 1.4. And it corrects for error. So it's pretty strong. So you have to break 5 machines to break one file.
When do you discover the files are corrupted?
The question is when do we discover the corrupted file?
So that's handled by the block fixer component. So we have a polling thread that finds out every minute the list of corrupted files. And for any new file that's found in the last 1 minute, we'll submit a MapReduce job to fix in.
So it's a scale job to do that?
So there will be multiple MapReduce jobs. So that's what Patrick worked on.
So you were referring the x-specific
So the RAID shell is essentially same, has the same code base as the block fixer. The block fixer is part of the RAID node daemon, whereas the RAID shell is a command line tool. So it has the same functionality as the block fixer, except that you can invoke it on demand.
The difference is just
Right, so it's the RAID shell. That's what we are. Okay.
So even for the on-the-fly block, you saw the app install.
Okay, so I think I misunderstood the question. So you're talking about the client file system that fixes it. So yeah, it's called distributed RAID file system. So it's a layer on top of distributed file system. And to fix a block there, it does reads the relevant blocks and computes the block on HDFS. So let's say you're reading a 10 gigabyte file, right? And at offset equals at a 1 gigabyte offset discover corruption. So the 256 megabyte block at that offset will be reconstructed, and the client will create that block onto the file system and resume. So basically, even though there are two pieces of the file, the client resumes reading at the newly constructed offset. So most of the time, the rated files are a little bit. So there are two factors here. One is that the files that we read are about 15 days old, so they are not absolutely hot. So it's not noticed by many clients. And because we have this block fixer component that identifies and fixes blocks within minutes, it's tough to say if a client actually notices a delay. So in practice, we have not had any warehouse user complain about latency because of this. Does that answer? Right. So if a map task encounters a problem, right? Yeah. So it would do the same work as a normal time, but again, it will not fix the block itself. It will just do enough work that it can continue work. So there are no user visible failures from rated files. So write is done the normal way. So there is no interruption when you write a new file. It's created as a regular replication 3 file. Now the RAID node will come after 15 days and we will see that a file can be rated, and then it creates the parity and reduces the rate.
So even you have separate RAID parity file system now, it's the normal data file system. But you are not going to guarantee full error correctly. Those case both file happen.
So the question is, how do we ensure that we have ensure we can correct up to 4 errors? So the approach we do is we spread out those 14 blocks on different machines and possibly different RAM. So if those machines die, they die with 1 block, and other blocks will survive. Thank you.